In this video, we'll cover the pitfalls of multithreading and how you can avoid them while programming. Multithreading is a great way to speed up computations, but if it's done incorrectly, you risk corrupting the state of your program. To give you an idea of what can go wrong in a multi-threaded program, let's look at an example. A bank is about to execute two money transactions. On thread 1, a transaction is being made from account 2 to account 1 for $300. On thread 2, a transaction is made for $400 from account 2 to account 1. If there are insufficient funds available, the transaction should not be allowed to take place, hence the if statement. Moving through the code of thread 1, we will detect sufficient funds, deduct the funds from account 2, and transfer them to account 1. Now, what could go wrong if thread 2 is being executed simultaneously? Here's one recipe for disaster. On thread 1, we have reached the line that deducts the funds, but it has not yet been executed. Meanwhile, thread 2 is evaluating whether we have sufficient funds for transaction number 2, and a quick look at our shared variables indicates that we have $500 left, which is fine, so it will proceed to execute that transaction, as does thread 1, and we end up with an account 2 balance of minus $200. Since account 2 only had $500 available, one of the two transactions should have bounced. Due to the order in which the statements were executed, both transactions were allowed to go through, which is not what should have happened. The problem doesn't end there. Even something as simple as a pre or post increment can go wrong. It may not look like it, but this simple increment is not a single instruction for the processor. In reality, the processor needs multiple instructions to increment the variable. If the increment instructions from thread 1 and thread 2 get tangled up, well, you might have a case of data corruption on your hands. Now, I'm not gonna bore you with assembly code, but here's the simplified version. To increment the value of a variable, the processor has to first load this variable from memory into its registers. Then, as soon as it's loaded into its registers, it can increment that register with 1 and finally write the resulting value back to memory. Consider this scenario. Thread 1 gets its local copy into a register, thread 2 does too. They both increment their register value and then try to write their register value back to memory. Regardless of which thread writes their value to memory first, the test value will always be 6 and not 7, which is what we would have expected. In the absolute worst case, your test value could become corrupted and then all bets are off. Long story short, multiple threads shouldn't be writing to the same variable at the same time because that causes problems. Much like traffic lights regulate access to an intersection, we need a mechanism that lets us control access to shared variables. Going back to our previous example, we need to identify so-called critical sections. In our program, we want to make sure that at any given time, at most one thread is using our shared variables. These will be our critical sections. If any thread wishes to enter their critical section, they will have to wait until no one is executing their critical section and then they get the go-ahead. In other words, any thread wishing to get access to the balance information has to request access and wait for their turn. Threads wait for their turn before they enter their critical section, and when they're done, they signal that they're done. Threads must do this. If they don't, other threads wanting to enter a critical section of their own will be kept waiting indefinitely. The technical term for this phenomenon is starvation. One more thing about the wait and signal operations. They are atomic, which means that they're immune from disruption by other threads. Let's see how this might go down. Thread 1 wishes to enter their critical section and requests access to the shared variables. They get the immediate go-ahead because no one is inside their critical section at this point. Now, while thread 1 is inside a critical section, thread 2 also wants to enter a critical section of their own. They call the wait function and they are kept on hold. After executing the transaction, thread 1 leaves its critical section by calling the signal function, which will then wake up thread 2. It will enter the if test and notice that there are insufficient funds available for the transaction, so it will bounce as we expected. Finally, thread 2 will leave its critical section by once again calling the signal function. It's perfectly possible that thread 2 is the first to enter their critical section. In this case, transaction number 2 will be executed, but transaction number 1 will not, due to, again, insufficient funds. We don't know in which order these transactions will be processed, but we do know that no two threads will be processing transactions simultaneously. You should always try to make your critical sections as small as possible. If all of your threads are constantly waiting in line to enter a critical section, well, then you're not going to get much of a performance boost. Here's another way to look at the wait signal mechanism. This shared resource can only be claimed by one thread at the same time. Thread 2 makes a claim on that resource and gets access. Now, thread 1 also makes a claim on that resource, but since thread 2 is using it, it is rejected. Then, when thread 2 is done with it, it will release the resource and thread 1 will get access. In rare cases, a shared resource can be used by more than one thread at the same time. In this example, a maximum of 2 threads can be using the same shared resource at the same time. Threads 1 and 3 try to access the shared resource, that request is granted. Now, when thread 2 tries to claim the resource, its request is put on hold. When thread 3 leaves, a space opens up and thread 2 can come in. The mechanism I just explained is called a semaphore. Semaphores that allow up to one thread to be executing a critical section are called binary semaphores. Now, when you're programming in a certain language, you'll most likely see the name mutex being used. Mutex stands for mutual exclusion. It's not exactly the same thing as a binary semaphore, but within the scope of this simple introduction they're roughly the same. So, when do you need to use a mutex? If you create and initialize a shared variable before spawning multiple threads, and only use these threads to read the value, then there's no problem. As long as none of your threads write to it, you're fine. If only one thread is using your shared variable, there's no way that 2 threads can disrupt each other's business. Again, no mutex is needed. If multiple threads are writing to the same variable, then you need to use a mutex. Whether your threads are actually reading the variable is irrelevant here. Once you have multiple writers writing to the same shared variable, you have to use a mutex. And finally, if you have at least one reading thread and one writing thread that could be active simultaneously, you also have to use a mutex. Right, that about wraps up the theory, but how do you put this in practice? I'll walk you through a couple of popular options. Please note that there may be subtle differences in the way that certain programming languages implement multithreading, so be careful. If you're working with C on Unix platforms, you may want to investigate pthreads. It's a low-level library, but it should get the job done. There's also a Windows implementation available somewhere. If you're fortunate enough not to be stuck with C, you should try QMutex from the Qt framework. This framework is available for Windows, Linux, and Mac, so all major platforms are covered. Oh, and also, their documentation is great. You can get the framework for free from qt-project.org. If you often find yourself working with the Boost library, then you should check out their mutex class. If you're a Java developer, you should look at the synchronized keyword. More information about that is available on Oracle's website. .NET developers should look at system.threading.mutex. More information about that is available on the Microsoft Developer Network. And finally, Python users should check out the threading module. More information about that is available on the Python website. This concludes my introduction to the dangers of multithreading. If there's anything you'd like to see explained on this channel, do let me know in the comments. Thanks for watching, see you next time.